All right. 1.1. We're talking about just an intro, terms, and definitions. So first off, we want to know what is a differential equation. It sounds very intimidating. A differential equation is just an equation that relates a function and its derivatives. I'm going to say a function or functions to one or more of their derivatives. So it's just some kind of equation that involves functions and derivatives. And we've seen some of these before. We've actually worked with a lot of them. For example, dy dx is x e to the x. That's a differential equation. Y is a function, and its derivative is x e to the x. And we know how to solve this. How do we solve something like this? Yeah, we integrate. So we'd say y is the integral from, the indefinite integral x e to the x dx. And that would tell us what that function is. And we'd have a constant of integration involved as well. Now our task, our goal in working with differential equations generally, we can't always do it, but generally we want to solve the equation in this case for y equals some f of x. That's what generally our goal for differential equations. Get y equals something. Well, often we'll get an implicit solution, so f of x, y equals something, and we'll see some examples of that. So we're going to talk about a number of types of differential equations. So I'm going to abbreviate it ODE. ODE is an ordinary differential equation. We usually abbreviate it ODE so we don't have to write ordinary differential equation over and over. And we'll also abbreviate differential equation just by DE, so we don't have to write differential equation each time. An ordinary differential equation contains derivatives of only one independent variable. So we could have something like dy dx equals 3xy plus cosine x. That's an ordinary differential equation. We have the derivative just in terms of x. Now this one we can't just solve by integrating because we have this y. We could have a second derivative, so d squared y dx squared plus dy dx equals 4y plus 3. That's an ordinary differential equation. We just have derivatives with respect to x. We have a first and a second derivative in this case. So this one we can't solve by integration. Or just by directly integrating. And and we can also have more than one unknown function. So we could have dx dt plus 5x equals dy dt plus 3y. So here we have our x as a function of t and y as a function of t. So we have more than one unknown function. We saw differential equations similar to this when we worked with vector value functions. Saw something kind of like this when we talked about the heat-seeking particle. We had a derivative with respect to x, dx dt, and dy dt, and we did some stuff to come up with, we actually integrated, we solved a differential equation there. So these are ordinary differential equations. We also have, we won't talk about them in this class, but we have what we call PDE for short, our partial differential equations. And they are differential equations that contain partial derivatives. So we're taking the derivative of some function with respect to x and y, or more functions, or more variables than that, depending on the function. So an example of a partial differential equation, it would be something like this: second partial of u with respect to t is c squared, d squared u dx squared plus d squared y, u dy squared. This is the wave equation. So a two-dimensional wave equation. So this would talk about how you could describe like ripples on a pond. It would be described by this equation. U might be the z value, the height above the equilibrium, or something like that. The heat equation is similar, but we just have a first derivative on the left-hand side. And that partial differential equation is the heat equation. And that would talk about U would be our temperature function, and that talks about how the temperature in some two-dimensional area, plane region, changes with respect to distance from the origin and with respect to time. Because the temperature can vary with respect to distance and with respect to time. So we won't deal with PDEs. Once you know basic ordinary differential equation solution techniques, it's pretty easy to move on to partial differential equations. And often partial differential equation solutions end up being some kind of thing that you do to turn the partial differential equation into a series of ordinary differential equations that then we solve using techniques that we'll learn in this class. And we're going to use dy dx and y prime notation. So they're kind of used interchangeably, or when one notation suits us better than the other. So we'll use both notations. This notation, the D notation, came from Leibniz, and the Y prime, the prime notation, came from Lagrange. And the Newton notation for time derivatives uses dots above the variables. All right, questions so far? All we're talking about in this class is ordinary differential equations. The order. Order of a differential equation refers to the highest derivative. So first order differential equations have a first derivative only. And we've seen first order differential equations written in differential form. Could have something like this: m of x, y, dx plus n of xy dy equals 0. That is a first order ordinary differential equation, and this is written in differential form. And we could rewrite this. We could divide everything by dx and rearrange this, and we'd get dy dx is negative m over n. So that would be written in derivative notation rather than differential form. But we saw these when we were talking about vector fields. Not necessarily equal to 0, but we talked about a vector or line integral in differential form, kind of similar to what we're doing. And we'll have a similar technique will come up when we have our differential equations written in differential form, to what we did when we talked about vector fields. So this is a first order ordinary differential equation. We could have something like y plus 2y dx plus x squared dy equals 0. If I divided everything by dx, I could rewrite this as y plus, I wanted an x in here, 2xy. Y plus 2xy plus x squared dy dx equals 0. That's another way we would see this same equation written. Just divide everything by dx. Now, when we divide by dx, when we divide by dy, we're kind of being very loose with the notation because there are certain conditions under which you can divide by that little dx or dy. We're going to say for now that all the conditions are satisfied that allow us to do that. Generally, the dy and dx are not fractions, but we can treat them like that in certain situations. This is one of the situations we can. And we could subtract we could isolate the dy dx if we wanted to. We could subtract this term from both sides, divide by x squared. We could have, just another example, cosine y dy dx plus 3xy plus x squared equals 0. First order ordinary differential equation. We could write it in differential form. I'm just going to divide everything, or sorry, multiply everything by dx. We'd get cosine y dy equals 3x, or sorry, plus 3xy plus x squared dx equals 0. These two ways of writing this equation are equivalent. But these are both first order ordinary differential equations. All right, good so far. So we can write these equations in this form. F some function of x, y, y prime, dot, 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 up to some derivative. The parentheses mean a derivative. The nth derivative of y equals 0. So some function of x, y, y prime, y double prime, dot, 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 up to however many derivatives we have, equals 0. We call this the general form of our differential equation. So let me go back here. Here our function would be our function of x, y, y prime equals 0. So this would be f of x, y equals 0. This whole thing would be f of x, y, y prime, y double prime, etc. equals 0. F of x, y, and y prime in this case. So that's the general form of our differential equation. And if we solve for this nth derivative, we could say the nth derivative of y with respect to x, and we get some function of y, y prime, y double prime, up to the n minus first derivative of y. And this should be we should have an x here also. X, y, y prime. Often we'll isolate the highest derivative. And we call this normal form. For first and second order derivatives, or sorry, differential equation, we can write it in the form dy dx equals some function of xy. And for a second order differential equation, we can write this normal form as the second derivative of y with respect to x is some function of x, y, and y prime. This would be the normal form of a first order differential equation. This would be the normal form of a second order differential equation. We just isolate the derivative, or the highest derivative. All right, so we have an ordinary differential equation at the order, which is the highest derivative. And now we're going to talk about linear versus nonlinear. And we'll talk about solving both linear and nonlinear. The linear ones are nicer. So for a linear ordinary differential equation, the functions and their derivatives appear to the first power only. And the coefficients are only functions of x. So we can write in general, we have a sub n x d n x dy dxn plus a sub n minus 1 x. We have the n minus first derivative here, plus, and we can go all the way down to a sub 1 of x dy dx plus a sub 0 y, a sub 0 of x, y equals some g of x. This would be a a linear differential equation of order n. Nothing, our derivatives and our functions only appear to the first power, and our coefficients are only functions of x. Now these a sub n's and this g of x can also be constants. A constant function is a function also. So an example, we could have the second derivative, d squared y, dx squared plus 5 dy dx plus 6y equals 0. This would be a second order because of the second derivative. Linear because the derivatives and the function only appear to the first power, and this is an ordinary differential equation. If we had something like 5 dy dx squared equals cosine of xy, x times y, that would be nonlinear because of this squared and because this coefficient, this function, is not just a function of x. It would be a second order ODE. We could also have something like this, 5y dy dx equals 6y. That is nonlinear because these are not just functions of x. So that's first order, nonlinear, ODE. Now, this one, even though it's nonlinear, this one turns out not difficult to solve. You can see how we would solve that one. you can divide by y, and then multiply both sides by dx, and then it's separable. You integrate both sides. We'll talk about separable equations. That's when we actually first start solving differential equations in section 2 of chapter 2. So that's 4 sections away. Yes.
Why is it? Does the squaring the first derivative make it a second order?
No. This would still be first order because it's still a first derivative, but it's nonlinear because we're squaring that first derivative. The order has to do with the derivative. If it were a second derivative, it would be a second order. But the squaring and this thing is what changes the linearity. Yes?
Wait, so on the side you said it was like nonlinear second order. It should be nonlinear.
Oh, first order, yes. Thank you. Now I understand why you asked that question. All right, so finally, now we're ready to actually talk about solutions. We're not going to actually solve them. We're going to talk about the solutions. So we need a definition. Our solution of an ordinary differential equation is a function f of x that has at least n derivatives and is continuous on some interval. And it has to satisfy the equation. So if we have a second order differential equation, we need this function to have 2 derivatives at least, and it needs to be continuous on some interval. That satisfies the differential equation. And this interval is important because all we need is for our derivative, our function to satisfy the equation on some interval. It doesn't have to be a continuous function everywhere. It doesn't have to satisfy the equation everywhere. It needs to satisfy it at some interval. It's called the interval of definition. The interval of existence. The interval of validity. Or the domain of the solution. So we can have a solution where the function that y equals f of x is defined everywhere, but the interval of validity for the differential equation could be only a small portion of the x-axis. So it could be, the function could be a function continuous everywhere, but we don't say that the domain of the function is all real values, because it might only satisfy the differential equation between -1 and 1, for example. So we say the interval of definition for that solution is -1 and 1. And we'll see that where that happens when we actually start solving these. So when we start solving equations, it'll ask us many questions. Will ask us find the solution and define the interval of existence, or the interval of definition. All right, so let's look at to verify. That y equals c e to the negative x plus x squared minus 2x is a solution to y prime plus y equals x squared minus 2. So when we're verifying a solution, we're just doing these derivatives, adding the derivative, add it to the function, and see if we get x squared minus 2. So we're doing the operations and see if we get doing what the one side tells us and see if we get the other side. So y prime. If we take the derivative of this thing, y prime is negative c e to the negative x plus 2x minus 2. And so y prime plus y is negative c e to the negative x plus 2x minus 2 plus c e to the negative x plus x squared minus 2x. And when we do all of this, we get x squared minus 2. We have verified that this, where is it? This is a solution to this differential equation. Because we did these derivatives, we added them together, and we get this thing. That's what it means when it says verify that we have a solution. Do the operations and see if it works. If y equals 0 is a solution, on some interval, we say it's the trivial solution. Y equals 0 and the trivial solution, that they mean the same thing. The graph of a solution function is called the solution curve. I'm going to say is a solution curve. And just so we know, after this first section is very heavy on a lot of terminology, a lot of definitions. It's not like that in every section. This, I always, in differential equations classes, this first thing where we're classifying and naming and talking about all these terms, it's not the most exciting stuff. But all of these terms come back repeatedly. Implicit versus explicit solutions. We have talked about implicit and explicit functions previously, so we have some familiarity with those. Y equals f of x is explicit, and f of xy equals 0 is an implicit solution. So often, our our solutions, we will not be able to solve for y in terms of x, so we will get an implicit solution. And you will have homework problems that ask you to verify that some implicit function is a solution to a differential equation. You just have to remember your implicit differentiation. You can do it the way we did in Calc 3, talk about implicit differentiation for f of xy equals a constant, or you can do it the way you learned in Calc 1. And you just do the operations and show that it works. In general, solving differential equations involves integration, and we get a constant of integration for each integral that we perform. So we say an nth order differential equation produces an n parameter family of solutions. So that we get the parameters are our constants of integration. We get one for each integration that we perform. So a second order differential equation is usually going to involve two integrations. So we get two constants of integration. We get a two parameter family of solutions for second order differential equations. A solution with no parameters is a particular solution. And for a particular solution, we need to know something about the values of the functions and its derivatives at points in the domain to solve for those constants. And finally, a solution.
Good morning, Monarch High School. Thankful everybody made it here safely today. We know the conditions out there are pretty bad. Now that we're here in the building, I did want to give a reminder to everybody that we are in the phase of having our distraction-free BVSD policy of no cell phones. So during the school day, students, you're to keep your cell phones away and off for the entire day. That does mean once you enter the building, throughout every class, every passing period, and yes, even during lunch, your phones are to be stored away somewhere, preferably someplace like your backpack, where you don't have that temptation to use it. It does include all spaces in the building. So that means the hallways, the library, cafeteria, even outside of the nicer days, we're sitting outside and eating lunch. So I wanted to give you this reminder of that. We're going to spend these first couple of weeks making sure we're all on the same page with how we're doing this, and give us an opportunity to see how the implementation goes. So before we got to that passing period, I wanted to make sure you knew that administrators will be reminding you. Teachers have been reminding you and still have the same expectations that your phones are put away either in the holder or in your backpack during class. At this time, teachers, if you want to, you can also show the video. Otherwise, students have an awesome day, and we'll see you in the hall.
All right, so the final thing is if we get we can find a solution, or a solution that cannot be found by solving for the constants, is called a singular solution. So, for example, for this differential equation, this is the solution, and we'll see later how to come up with this solution. While y equals 0 is also the solution to this equation. We can see that by substituting that in. Derivative of 0, 0, 4 times 0, 0. But we can't get that by substituting for some value of the constant here. So we call that a singular solution to that differential equation. All right. That's a lot of terminology. Our homework. This is section 1.1, page 12. All of that stuff is in 12 pages of the textbook. That's not a lot of pages.
You're on page 1,000. You've bounced so far.
There we go. Same homework policy that I had last semester. I'll collect homework once a week on block days. Again, I would strongly encourage you not to wait and do all your homework on Wednesday. And I think you'll find the types of problems that we do, the type of thinking that we do, very different from what we did last semester.